All right, in this video, we are going to introduce surface integrals of scalar functions. Okay, so here I have a parametric surface S in R3, and it's parameterized by this vector function R, and the domain of R is this region capital R here in the UV plane. And here on the surface, I have a bunch of what we called U traces in red and V traces in green, right? Those are just the images of these horizontal and vertical lines um, under this vector function R. Okay, so what we're going to do here is say, consider one of these little differential rectangles that's formed by this grid here. And we're going to map it over under our vector function R to this little piece of surface area along our surface S. Okay, and we're going to call this little differential surface area element ds. And we want to first derive an expression for ds in terms of this parameterization R. Okay, so to start here, we'll go ahead and zoom in. Now over in the domain R, okay, this is just a differential rectangle. And so the width here is just a little differential change in u, so that's du. And likewise here, we have a little dv change there for the height of the rectangle, and its area is dA. Now over on the surface, okay, when we zoom in, we're going to see this little parallelogram that's formed by these U-trace curves in red and the V-trace curves in green. Okay, and I drew in these blue, uh, or this blue vector and this yellow vector here. Okay, and so what are these things measuring? Well, if I increase U a little bit, right, this differential amount du, then my position vector is going to change from this position right at R of UV to this position right here, where I'll end up right after I've changed U this amount. Okay, so this vector in blue is just measuring the difference then in these position vectors. And likewise for the yellow vector, okay, if I change V, this differential amount dV, then this yellow vector is just going to measure that change in my position along this V trace. Okay, so now I argue that this blue vector here is simply the tangent vector tu that we introduced in the last video times this little differential change du. Okay, and a way to think about that is that, well, this difference vector is just describing right the change in my position, and this tu vector, that's just telling me the rate at which I'm moving along this u trace. It's just my velocity, and I'm going to multiply that rate by this incremental change, in this case of u. So if I think about u as, say, measuring time for the moment, and this is my velocity, I'm just really saying velocity times this little change in time is going to tell me, right, that change in position along the u trace. Now, if I want to get a little more formal about it and use limits and that sort of thing, well, tu by definition is the partial derivative of our vector function r with respect to u. And so, put another way, the difference vector you see up here in the numerator is at least approximately equal to, right, for small changes of u, it's approximately equal to this tu vector times delta u. Okay, so on the differential level, then this is what we're going to get, which is tu times du. And likewise here for yellow, tv times dv. All right, so now you got to remember something from Calc 3, right? I have this parallelogram that's formed by these two vectors. How do I find the area of the parallelogram formed by two vectors? Oh, okay, well that was the magnitude of the cross product of those two vectors. So we can now say that this differential change in surface area, ds, is the magnitude of the cross product of the blue and the yellow vectors. And I'll go ahead and pull the du and the dv out in front, and that is just dA. So I get that the, again, differential change in surface area, ds, is equal to the magnitude of the cross product of these tangent vectors, tu and tv, times the differential area element over here in the domain, right? It's just my dA there. Okay, now, of course, in the last video, we spent a fair amount of time deriving this expression for various parameterizations, and we're doing that in anticipation of what's to come. It's going to help simplify some of the calculations we're going to do. Okay, so let's now go ahead and define a surface integral of a scalar function, okay, over some surface S. Now here, you want to think about your scalar function f as measuring something like, say, mass density. So if f measures mass density, and I multiply that by a little change in surface area, then this product is just going to tell me the mass occupied by this little region. And if I sum those up, sum up the masses as you vary over the surface, that's going to just tell you the mass of the entire surface, right? So, if I think about this surface as some, thin metal plate that's been, uh, you know, uh, bent into some particular shape, then this thing is just going to tell me the mass of that metal plate. Okay, now this expression that follows is just telling you how to compute this surface integral in terms of this parameterization R. And it looks kind of bad, but actually it's oftentimes not too bad to compute. Okay, so all this is saying is just, okay, replace x with the I component of the vector function R, right? It's just what is x in terms of the parameters u and v, and likewise for y and z. And then here, ds, as we just argued here, is just that magnitude of the cross product of your tangent vectors times dA. And notice here, this double integral is over the region in the uv plane, right? It's an integral over the domain here. And dA here is referencing the differential area element over here in the UV plane. Okay, so two notes and then we're going to wrap up. So here, first, if f is just 1, then you're just taking the integral of ds itself. Okay, and that's just going to tell you what? It's just telling you to sum up a bunch of these differential surface area elements as you vary over the surface. So that sum is just going to tell you the surface area of S itself. Okay, and that's analogous to what we saw when we talked about, say, uh, double integrals of just dA, where we're looking at some region in the xy plane, and we said, well, that's just the area of the region. Or when we looked at triple integrals of dV, right, that was just the volume of the solid we were integrating, right? This is same idea here. Now, second note here is that for an explicit surface, so z is equal to g of xy, all of this up here becomes, well, what? Well, I'm just going to replace z with g of xy, and the magnitude of this cross product vector here, we computed in the last video, right? That was the root of 1 plus the partial derivative of g with respect to x squared plus the partial derivative of g with respect to y squared, and then we have our dA. Okay, so this can um, lead us to a calculation of one of these things pretty efficiently. Not to say this integral is going to be easy, but it's at least in principle not terrible to set up. All right, well, let's get to computing some of these things now, and we'll start that in the next video. I'll see you there. Thanks.